Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Before we begin, a note from our sponsor. I'm Richard Jacobs, Executive Director of the nonprofit Finding Genius Foundation and host of the Finding Genius Podcast. In late 2016, I was rear-ended at 65 miles an hour by a truck on the highway, which sent me off-road into a ditch. The impact of the collision gave me a concussion and other injuries. At the hospital, a CT scan showed that I had thyroid nodules, which turned out to be cancer. It was then, when I had a biopsy of my neck, that I realized even if I was a millionaire, I wouldn't want a second or a third biopsy due to the pain and the invasiveness of it. And appointments at that time for thyroid experts were 3 to 6 months out. And I was worried about dying now, even if that was irrational. So because of this, I've decided to raise money to conduct a literature review on steroids, on the causes of anxiety and depression, a condition that affects well over 50 million people in the United States and hundreds of millions worldwide. Our goal is to create a codex, a guide that reveals all possible treatments for anxiety and depression for people that live with the condition, or for loved ones that have it, as my wife and my son do. To find out more about our fundraiser, visit findinggeniusfoundation.org and click on current initiatives. And now to our guest.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Moritz Lehmann. He's a PhD candidate in physics. He's at the University of Bayreuth, located in Germany, and we're going to talk about microplastics. So Moritz, thank you for coming.
Hi, thanks for having me.
Yeah, no problem. Tell me, I've interviewed a number of people about microplastics, but for people that don't know, what are microplastics and how are you studying them?
So microplastics are tiny fragments of plastics that are found in the environment, mostly from degrading plastic waste that somehow ended up in the environment. And it's really hard to get rid of them. And they don't really disappear. They just break up in smaller and smaller pieces, and they are everywhere. And that's a real problem. Yeah, what got me into microplastics, it's a bit of a longer story, because I had a little idea about microplastic when I started my studying at the University of Bayreuth. So my background is I'm a theoretical physicist, but I'm also a programmer at the same time. So I write my own software.
Oh, cool.
And when I did my bachelor thesis, I got to the biofluid simulation and modeling group, and we did blood flow simulations there with a Lattice-Boltzmann software. So this got me into computational fluid dynamics. However, the software that we used at the time was rather slow. It took several weeks to do most of the calculations. So I started writing my own Lattice-Boltzmann CFD software from the ground up. And because I did it in the OpenCL framework, which is GPU programming, it turned out to be that my code was much faster. And so I kept going, and it eventually turned from a hobby into my master thesis. And then during my master thesis, the possibility arose that I could do my PhD at the Collaborative Research Center, the CRC 1357 Microplastics. It's a research project funded by the German Science Foundation. And the CRC Microplastics is all about studying microplastics in the environment, the properties.
Right. What does that mean specifically? What do your models do? I don't understand yet. What are you modeling?
Yeah, so I'm modeling fluid flow, so the Navier-Stokes equations from a physical point of view. And my software is specifically designed to do to simulate water surfaces, so moving water surface with surface tension. So, for example, I do impacting raindrops and simulate the splashing, and then look at if microplastic particles can be transported into the tiny droplets that then end up in the air.
Are you saying microplastics, they aerosolize? What do you mean? What happens? Where?
Yeah, that's the thing that I'm trying to find out, and it's a really tough and difficult question. So the microplastics in the ocean, they are present everywhere, also in the ocean water, and there's a so-called sea surface microlayer. So at the very surface of the ocean, there's a higher concentration of particles. And what I'm looking at, if it is possible somehow for these particles that float at the ocean surface in the water to somehow transition into the atmosphere. And this is a really tough question to get information about. You could do it experimentally. That's also what we're doing in the CRC. I have a colleague, Lisa Marie Oeschlägl in Berlin at the Technical University there. She's doing experiments on this. And I'm doing simulations. So I'm looking at it from a computer simulation part. So in experiments, you always have limited information. You have to do high speed images and then do maybe fluorescent particles. It gets really difficult to get sufficient information. I'm looking at it from the computer simulation point of view. And in the computer simulation, you have the big picture, you know everything. And in my simulations, I did impacting raindrops. So I basically shooted raindrops at a water pool and then looked at what happens when the water is splashing upwards, when the spray droplets are generated. And during this impact, at the perimeter of the impact site, the fluid shoots up very fast and then separates into hundreds of tiny droplets. And I found out that the microplastic particles, if there's any floating around at the sea surface microlayer, they do end up in these tiny little droplets. And in the concentration in the droplets is actually very, very similar to the concentration in the ocean surface. So this was another thing that wasn't clear from the beginning, because the raindrop that hits the water, the raindrop is devoid of particles. And it could be that the fluid of the raindrop somehow ends up in the spray droplets, but this is not the case. The majority of the spray is actually ocean water. Yeah, so we found out.
So you're saying that microplastics get entrained in droplets.
Exactly.
So this could happen if they're near any water. What about on dust? Have you modeled that to see if they're picked up by dust?
So with dust particles, I would assume it's very similar. In my computer simulations, the particles themselves had rather a limited set of properties. I could, for example, give them a density, and they had some sort of hydrodynamic interaction. However, you could substitute them easily with dust particles. However, the difference is that in the long term, dust particles have a higher density. So in the water, they tend to sink, whereas microplastics have a density similar to that of water. So they tend to float at the surface.
Have you been able to model how a large piece of plastic breaks up into micro? Able to model how they break up and then the types of shapes that are energetically preferred of the microplastic pieces?
No, I didn't look up at the breakup specifically. I focused on what happens if the particles have already broken up into these tiny microplastics, and then what happens to these tiny microplastics.
Do you think that modeling would be useful to figure that out? And what would be your speculation on it?
Yeah, it would certainly be a very useful insight to know how exactly the plastics break up. Currently, we think that it is due to several processes at the ocean surface. Specifically, there's like wave action, the surface is moving, and there's a lot of solar radiation hitting the plastic, so it becomes brittle over time. And due to the movement, we expect it to break up, but we also have little insight on how it specifically works. But I focused more on what happens if there's already these tiny microplastic particles, and how mobile are they, and can they transition in the air? And the answer to that is yes, and that is really surprising.
But what do you notice about the shape and the charge of these microplastic pieces? Do they tend to bond preferentially with hydrophobic or hydrophilic elements? I mean, what about the chemistry side of it? What do you notice?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show. So
in my simulations, I could do really limited parameters on the properties of the microplastics. I couldn't give them like a surface charge. The only thing that I modeled was that they like cannot exit the water right away and sort of jump out of the water, which is unphysical behavior. You would expect them if they are at the water surface to stick to the surface and not leave the water phase by themselves. Only if the droplets can fully evaporate, then the particle sort of floats free in the atmosphere. But on the chemistry side, besides the sticking to the surface, I couldn't really model a lot in the simulation because the model it's difficult enough. And as a physicist, I always try to find the simplest model that sufficiently captures what's actually going on without overcomplicating things, and to have a model that is reproducible and simple enough. With the impacting raindrops, the difficulty there was that you have like a raindrop impact at the entire scale is several centimeters. And on the other hand, you have these microscopic particles that are tens of micrometers in diameter. So you have, on the one hand, you have tens of micrometers, and on the other hand, you have tens of millimeters. That is 3 orders of magnitude in scale that you're trying to resolve in simulation. And that requires gigantic amounts of memory, and the memory is rather limited on the computer systems, especially on graphics cards.
But are you able to, so that would be if a plastic is already broken down and then it was exposed to water. I could see how the water again would carry it and aerosolize it, etc. But does anyone have any insight on how a plastic bottle, for instance, starts to break up to form smaller and smaller pieces, and how many cycles, like if I take, again, a plastic bottle, when it first breaks, does it break into pieces that are, an inch size across, or, 100 millimeters, or, 20 millimeters, and then it breaks again, typically into 5 millimeter pieces, and then it breaks again? Like, how many cycles of breaking has anyone been able to estimate that?
I can't really give you information on that, as I don't really know myself. I only know that you find the microplastics, so that is the output, and the input is the plastic waste that flows into the ocean via the rivers, for example. And in between, there has to be a process, as you say, that the plastic bottles break down in steps to smaller and smaller pieces. But I don't know how specifically that works, but it's also subject of current research. There's experiments going on with weathering plastics and trying to find out the properties. Also, the chemists at our CRC are working on that.
Is anyone modeling that? Do they have like a tank that agitates back and forth with plastic bottles in it, and they put in ultraviolet light and they try to recreate conditions in nature? Do you know any labs that are doing that to try to break apart these things to see how they break apart?
I don't know specifically at our CRC. I don't think we are doing these experiments with macroplastics and the transition from macroplastics to microplastics. We are more focused on what happens when the plastics are already tiny. But we have a lot of scientists interdisciplinarily researching on the properties of the tiny particles then. For example, also the chemists and the biologists, they focus a lot on the eco-corona of the particles. So on the microplastic particle surface, they tend to stick, biological molecules tend to stick to the particle surface. Not only molecules, but also microorganisms, if they are small enough. And this changes the physical properties of the particles, how they behave in nature, in the transport processes, and also especially how they behave in a biological way. For example, another researcher, Anja Ramsberger, found out that the weathered microplastic particles, when they have an eco-corona, they do something like the Trojan horse effect. So microorganisms see the particles and think the particles are food because they are covered in biological molecules that look like food to the microorganism. And then the cell tries to eat the particle and engulfs it via endocytosis. But then the particle is stuck inside the cell, and the cell can't digest it and can't throw it out anymore. And it inhibits some of the mechanical functions of the cell and some of the well-being and the growth of the cells. So this is still very much current research going on there to find out the biological effects of microplastics as well.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Through your modeling, though, you see that they're readily taken up and entrained and spread. What does this tell you about where these plastics could go that maybe no one contemplated?
Yeah, so the current findings, also from my research, are that microplastics are extremely mobile in the environment. They can go from anywhere to anywhere else on the globe, which is really surprising. So microplastics have been found in Antarctica. They have been found at the top of Mount Everest, in places where no people live, and still microplastics end up in these places. And the proposed mechanism is, of course, atmospheric transport. So once microplastics are in the air, they are so tiny, the particles, that they can stay afloat for very long periods of time and can be transported across very, very, very long distances. And I think it's a very similar process to how dust aerosols are also transported. For example, right now on my windowsill, there's dust from another continent, from Sahara. There was large dust plumes this week coming from the Sahara across Europe, and the sky turned like yellow, and it was a bit crazy. But this shows that it is possible that tiny particles can be transported across thousands of kilometers by the atmosphere. And microplastics also follow these criteria. They are extremely tiny and can stay afloat for a very long time. And the part that I really focus my research on is if it is possible that these microplastics in the air do not only come from terrestrial sources, like, for example, the sand in the Sahara only comes from terrestrial source, but also from marine sources, from the ocean surface. Because previous research has already suggested that the ocean might be a source of airborne microplastics. Steve and Dee Allen have found that plastics in the air come especially also from the ocean when the wind blows in from the ocean across the coast. And this suggests that there must be some process going on that the plastics can transition across the water surface. So one process I already told you about is the impacting raindrops. And currently I am working on simulating a second process, which is bursting air bubbles. So when there's movement at the ocean surface and breaking waves, and there's bubbles entrained in the water, and then the bubbles rise again to the surface. And when they then arrive, they burst and pop. And there's two processes actually at play that can generate tiny droplets. The one is film droplets. So like from a soap bubble, when the film tears apart, it creates tiny droplets. This is for the larger bubbles. And for the tiny microscopic bubbles, there's a jet emerging. And this tiny microscopic jet produces one or even several tiny droplets. And it could be that microplastics end up in these tiny droplets. And this is what I'm currently also investigating.
So what's, I don't know, what hypotheses are you testing with your research going forward?
Yeah, I'm looking if the spray droplets are transport vehicles, are possible transport vehicles for the atmospheric transition. And it is not as straightforward as it sounds, because for the raindrops, I did a secondary analysis of the droplets. So the simulation provided me with statistics. I simulated many hundreds of impacting raindrops, each generating several hundreds of droplets. And I know for every one of these droplets, the size and the speed and how many particles are inside. And with this data, I did a secondary analysis. I simulated the trajectories of the droplets in the air, accommodating for evaporation and for different wind conditions. And what I found out was that the larger droplets, they just fly up and then fall down to the ocean surface and no transport happens. However, the tiny droplets, the small droplets can be carried on by the wind until they fully evaporate and only the microplastics stay behind. And for raindrops, I already showed that this is possible, that there's a fraction of the droplets generated is within the size range that they can fully evaporate. And for the bubbles, I'm testing the same hypothesis. So if there's droplets generated that are small enough and microplastics can get into these droplets, then it is very likely that transport actually happens.
Okay, very interesting. Well, very good. Moritz, what's the best way for people to find out more about your research? Where can they go?
So you can find me on the university website of the Biofluid Simulation and Modeling Group. I'm also on the website of the CRC Microplastics. That's CRC 1357. And to reach out to me, I'm also on Twitter and on YouTube with the name Project Physics with an X at the end. On YouTube, I do a lot of fancy videos of my simulations so that people can actually see what is going on. So that it's not a black box and you can see graphically what the computer is doing.
Oh, very cool. Okay. Well, Moritz, thank you so much for coming on the podcast. I appreciate it.
Yeah, thanks. A pleasure.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.